Have you ever wondered why you fall back when the MTR starts moving and fall forwards when it stops?
To understand this, let's go back to 1687 and visit Isaac Newton.
Unless acted upon by an unbalanced force, objects keep doing what they are doing.
In other words, if a body is at rest, it will remain at rest. If a body is in motion, it will remain at the same velocity, which means same speed, same direction.
This is Newton's first law of motion, also known as the law of inertia, the tendency for objects to resist changes in their state of motion.
All objects have inertia, but some have more than others. This is determined by their mass. The more mass an object has, the more inertia.
The amount of inertia determines what happens to an object when a force is applied to it. The more inertia, the more resistance to a change in motion. The less inertia, the easier it is to change motion.
Remember, a change in motion is caused by an applied force that overcomes the object's inertia.
Let's apply this. There are two identical boxes. How could you tell which one is empty or filled without lifting them? It's simple. Give them an identical push. The one with the least resistance has the least inertia and therefore a lower mass, meaning that it is empty.
Let's go back to the question at the start. Before the train starts moving, your body is at rest.
When it accelerates, your body tends to remain at rest because of its inertia. However, the train's movement causes there to be an opposing force acting on your body, which overcomes your inertia and causes you to fall back.
When the train is moving, your body is also moving forward with the same velocity. When it stops suddenly, your body tends to continue moving forward due to its inertia.
Inertia exists in many forms. What we just described was linear inertia, which resists changes in linear motion, the changes in speed or direction of motion in a straight line. Rotational inertia resists changes in rotational motion, the changes in speed or direction of rotation around an axis.
The concepts are similar, but here an object's inertia is determined by not only its mass, but also its shape and distribution of that mass around the axis of rotation.
Objects with more mass or more mass concentrated farther from their axis of rotation have more rotational inertia and are harder to start or stop rotating.
For example, a figure skater pulls their leg in so more mass is around their axis of rotation, causing them to spin faster.
Lastly, there's gravitational inertia, the resistance of changes in motion due to the force of gravity.
This is why heavier objects are harder to lift. They have more mass and therefore more gravitational inertia. This means it'll be more difficult to move due to gravity.
Gravitational inertia not only affects our lives on Earth, but also what happens on a cosmic scale.
It's the reason why planets orbit the sun. The sun provides a gravitational pull, while the planet's large mass and gravitational inertia make it difficult to change their motion due to gravity.
Inertia is more important to us than we realize.
It's all around us, everywhere, every day.
Feeling hungry? How about an omelet? Inertia keeps the mixture moving in the same rotating motion to mix the ingredients.
Time to go to school. Because of inertia, the door keeps moving in the same direction until the door frame stops it. But inertia is also so much more.
Let's look at the bigger picture.
Special relativity, developed by Albert Einstein, is a concept that revolutionized our understanding of space, time, and the nature of the universe.
It's based on two postulates. 1. The laws of physics are the same for all observers moving at a constant velocity relative to each other.
2. The speed of light is the same for all. These led to important consequences, including mass-energy equivalence. According to the famous equation E equals mc squared,
mass and energy are both but different manifestations of the same thing.
Mass and energy are equivalent and are converted into each other through the conversion factor of the speed of light squared.
This incredibly large number means that a very small amount of mass may be converted into a very large amount of energy.
As an object moves faster, it gains kinetic energy. According to E equals mc squared, its mass also has to increase to conserve the total energy. Don't worry, this mass increase is negligible at everyday speeds.
Unfortunately, for aspiring space travelers, this is why you can never travel at the speed of light.
Even if an object 1,000,000 times lighter than an electron approached the speed of light, its relativistic mass and therefore inertia would become infinitely large.
This means an infinite amount of energy would be needed to overcome its inertia and accelerate the object to the speed of light.
This is why the speed of light is the ultimate speed limit of the universe.
Inertia keeps things at rest or in motion.
It's a fundamental law, an unbreakable notion.
It's all around us, every day.
Resisting change in every way.